So welcome everybody to the first episode of the 2024-2025 Colloquium series at the College of Optical Sciences. We have a wonderful lineup of speakers this year, thanks to our Colloquium chair, Daniel So, and the co-chair, which I believe is Florian Willemetzer. For tradition, we're going to start the first month with our new faculty members. And so it's a pleasure of mine, really, to introduce our first speaker, Felipe Guzman, who has arguably the distinction of being the first faculty member to join our department twice in the same 6-year time span. So Felipe is a Tico. That means he's a guy from Costa Rica. He got his EE, electrical engineering degree, bachelor's from the University of Costa Rica, went to Germany, where he got his master's in Oldenburg, and then he got his PhD at the Max Planck Institute of Gravitational Physics in Potsdam, where he developed optomechanical technologies for gravitational wave interferometry and for the GRACE mission, which we'll hear about today. So he took these technologies with him to the US. He did postdocs at NASA Goddard and at NIST Gaithersburg, and he went back and became a group leader at the German Space Agency in collaboration with the University of Bremen. So in 2018, Felipe joined the College of Optical Sciences as an associate professor. 3 years later, he moved to the Texas A&M University. And 3 years later, much like in the biblical story of the prodigal son, he had sort of squandered his wealth, survived a famine, and came back, where we welcomed him with open arms and awarded him with the Jack Jewell Endowed Professorship. So the reason for this is because Felipe's optomechanical technologies have become more and more powerful over the years. These are basically compact, monolithic optical interferometers, which he uses for inertial sensing and accelerometry and gravimetry, which are all words for the same thing. Arguably more interesting, however, is the future applications of these devices. He uses them potentially for space-based geodesy, for satellite inertial navigation, and arguably the coolest optomechanical experiment, to me at least, the space-based gravitational wave interferometer called LISA. So Felipe is a good friend of mine. I'm very happy that you're back. I think we're all very happy to have you back, Felipe, and we look forward to hearing again what you'll be bringing to the university.
Thanks so much, Tal. I couldn't really hope for a better introduction than this. This is fantastic. Thanks, Tal. And in addition to the wonderful introduction, you also spare me a slide, so I'll just keep going. So it is wonderful to be here again and to speak at the Colloquium again, because of many reasons. It's a wonderful place, the OSC. I think it's really a home, not just for me professionally, but for everything that we do in my group. So I hope that you enjoy what I have to say today. So I've broken up the talk in 3 parts. I'm going to be talking mostly about optomechanical or optical technologies in general for applications in astrophysics, earth sciences, and also planetary sciences. I see a lot of familiar faces that it seems like we're meeting in this very room very often. So I hope that you enjoy the venue. So first of all, let's start with gravitational waves. Gravitational astrophysics, really what we do. So let's go back to a little over 100 years ago when we got a new model for gravitation, right? So Albert Einstein came up with this idea, this model, that gravity is by itself an effect of the geometry of space-time. So we're used to the 3-dimensional space that we live in. We also have now the notion that time is by itself also an additional dimension in this geometry. And gravity is just how this geometry deforms based on the masses that reside in it. So if you imagine that space-time, just for simplification, imagine it's like an elastic band, a bed sheet. You wake up in the morning and hopefully you're good and make your bed nice and neat. And then suddenly you put a ball in your bed. You see how it deforms, it bends. If you put a set of balls and spin them, they'll start revolving around each other, creating little vibrations in that bed sheet, right? And those vibrations will spread out throughout your bed, which is space-time. And those are what we call gravitational waves. So by itself, general relativity is kind of intuitive. It is really just that. Now, mathematically, it is difficult to get to any absolute solution, aside from the very basic wave solution, the wave equation in general relativity, which gives you, as a result, gravitational waves. So these are oscillations of spacetime itself that spread out throughout the universe in the presence of accelerated masses, very large masses. This is, for example, a little video, a little rendering of the very first observation that LIGO made back in September 2015. It's almost going to be 9 years from that observation, actually next week, next Saturday. So these are two, moderate mass black holes, a few solar masses each, revolving around each other. As they rotate around each other, they are not, well, they're emitting energy in the form of gravitational waves because the system by itself is kind of losing energy. Angular momentum is preserved, so they need to start coming together. And at some point, they're just going to merge, right? Creating a new, larger black hole. Now, the larger black hole is not just going to have the mass of one black hole plus the mass of the other black hole, right? E equals mc squared. There's going to be a lot of mass or a significant amount of mass lost as it is irradiated in the form of gravitational waves. So something fascinating about gravitational waves is the fact that they actually tell us or offer us a different way to observe the universe. Particularly being here in Arizona, in the College of Optics, also very close to the Stewart Observatory. We're very familiar with optical telescopes, visual telescopes, IR, X-rays, all kinds of neat and fancy stuff. Now, they all rely on the observation of some type of electromagnetic wave, right? Some type of light. This is something completely different. And because of that, it enables a different way to explore and probe the universe and try to understand better what's really going on. So fast forward a couple of years after that very first detection, we were, in my opinion, very lucky to have been able to observe what we call a multi-messenger event. We call it multi-messenger because in this particular case, we have two neutron stars, again, rotating around each other, emitting energy out in the form of gravitational waves, getting closer, and at some point they're going to merge, in this case, creating a moderate mass black hole. Now, because of the nature of these objects, they in that merger, they will also irradiate a light signature that we were able to pick up with optical telescopes. So the reason why I think, or in my opinion, we were kind of lucky in a way to have observed this event is because, as we'll see in a moment, the signature of the gravitational waves is just a fraction of a second. And in a very short amount of time, we need to inform all the other telescopes and say, hey, somewhere in the sky, we've picked up possibly a candidate of a gravitational wave event, point that way and try to pick up the electromagnetic signature. And we did. And LIGO in particular, so this was observed by LIGO again, LIGO particularly isn't really good at determining the sky localization of the events. So now, how do we observe gravitational waves? We actually do it with optics. So many of you, hopefully most of you, are familiar with what a Michelson interferometer is. Now, before we go into the interferometry part, let's imagine that we have an array of masses, inertial masses, just sitting there still in spacetime. So we have these little black dots that are inertial masses, unperturbed. And suddenly, here comes a gravitational wave going into the screen, and the whole array starts oscillating. So what actually happens with gravitational waves is that they change the distance between the objects. So one side of this circle is going to get squished, the other one is going to get stretched periodically in a quadrupole manner into different polarizations, the plus polarization and the cross polarization, as you can see here. Now, how can we determine or how can we measure that displacement? And if you imagine that we can place for example, one mirror here and another mirror here, that is a Michelson interferometer. So something like this. And at the pass of a gravitational wave, if we align that Michelson interferometer to give us a 0 phase output at the detector, then that length relationship between the mirrors is going to change, giving you a phase shift that you can actually detect here at the photoreceiver, right? That is a very simple concept, not that easy to put in practice, as we'll see in a moment. LIGO is a very complex set of Michelson interferometers. It's not just one interferometer. We actually need 2 sites here in the US to be able to observe gravitational waves. And that Michelson interferometer that we use for LIGO has arm lengths of 4 kilometers. Something else to consider is the fact that how much are these masses going to move? So gravitational waves are produced by these extremely massive cosmological objects. How much is this going to shift? And the measure for that is what we call strain. So it is basically the delta L, the little shift in displacement of the test mass with respect to the baseline of your detector, the L. So of course, the larger the L, the larger the length of your detector, then the larger is going to be the shift that you observe in that detector, in the path of that gravitational wave. Now, as you can imagine, here on Earth, we have practical limitations on how large we can make those. We're actually pushing those farther and farther. But so in the case of LIGO, it turns out that having a 4-kilometer detector, we need sensitivities in the order of 10 to minus 20 meters to be able to observe a gravitational wave. So historically, since we started, since the community started working on LIGO back in the early 90s, for the longest time, there was a lot of concern of whether these waves were really real, physical, whether they were observable at all, because we had invested so much time and effort building this exquisite set of interferometers that were observing noise better than anything else we've built on Earth. Until, come early 2010s, we invested in a major upgrade of technology in the LIGO sites, better suspensions to isolate these test masses, better lasers, better optics, and so on. And during the commissioning phase, sometime in the mid-2015, summer 2015, boom, we observed this very first event that I showed you in the previous slide. Okay, so let's keep going. We have 2 sites here in the US. We have one in Livingston, Louisiana. You can see here in the aerial view, 4-kilometer arm length. This is the main building, the beam splitter here. It's housed in this location. This one is in Hanford, Washington State. They're about, I think it's 3,000 kilometers apart. So it's a significant distance apart. And the reason why you need at least 2 to be able to tell that you've observed a gravitational wave is because, again, these test masses need to or will be moving only in the order of 10 to minus 19 meters or 10 to minus 20 meters. Anything will make them move more than that. An earthquake, the pass of a train, even the wind blowing on the sites will excite the interferometer more than an actual gravitational wave. So there is a significant amount of work that we invest in the development of seismic isolation, active seismic sensors. And now that I mentioned seismic sensors, I go back to what Dal mentioned, basically accelerometers, inertial sensors. And that's where the research in my group comes in. I'll get to that towards the end of the talk. So just diagrammatically, we have here the US. This is LIGO, Louisiana. This is Washington State. There's about 10 milliseconds travel time between the 2 sites. So they're pretty far apart. This is on this axis, the strain sensitivity. So delta L over L. In order to observe gravitational waves, we need a strain sensitivity in the order of 10 to minus 23 here on ground. in the audio band, so above 10 hertz, all the way to a few kilohertz. This is kind of a concept drawing of the Michelson interferometer that we use for LIGO. We use also Fabry-Perot cavities in each arm to amplify the optical power there. This basically helps us beat the shot noise limit, increase sensitivity. There are many things that we're not including in this diagram to keep it simple, as you can imagine. But of course, if you take this strain sensitivity and convert it to displacement by the arm length of the interferometer, 4 kilometers, you get to that displacement sensitivity that I mentioned of 10 to minus 20 meters. It's pretty challenging.
What's the reflectivity of the test mirrors?
Oh, now you asked that question. I couldn't quote necessarily how many nines there are, but it's fairly high. So, well, actually, what I can tell you though, and you can do the calculation, is that this intracavity here, so this Fabry-Perot cavity here, has a finesse of a few hundred. I think it's about 300. That is the effective finesse. Now, that's not necessarily the entire, or going back fully to the coatings. There are some other losses, but that is the effective finesse that we get. Yeah. All right. Now, the entire community and worldwide has worked on developing more gravitational wave detectors. So we have the two LIGO here in the US. We have VIRGO in Italy. It's a French-Italian observatory. We have let's call it a test detector, Geo 600 in Germany, Hanover, Germany, near the institute where I did my PhD. This has been actually very instrumental to develop technologies that would then go off and be implemented on LIGO and VIRGO and other sites. Geo by itself doesn't really have the necessary sensitivity to detect gravitational waves, but it's been fantastic to develop the technology that led to the detection of gravitational waves. So I mentioned the major upgrade that LIGO underwent in the past decade. So a lot of that hardware, that's still fantastic hardware, is now being transferred to India to set up another site in India. There's also another, let's say, higher generation, let's say, fancier technology detector that is being set up in Japan called Kagra. And fancier technology in the sense that this detector is, for example, set up inside a mountain. It's using cryogenic technologies. It's using a lot of really novel stuff that could yield or will yield, hopefully, higher sensitivities. And those are the upgrades that we're thinking for the future generation detectors, such as the Cosmic Explorer here in the US. This is a future generation gravitational wave observatory we're already working on for the US. It'll be a very similar concept to LIGO. Instead of 4 kilometers, we're thinking of 40 kilometers arm lengths. Then the Europeans, of course, are not falling behind. They're going to build an underground detector in a triangle configuration. The arm lengths are going to be shorter. They're going to be about 10 kilometers. But it's also going to be working with cryogenic technologies and such. Cosmic Explorer is not really going there. We're going to go for longer arms. The Europeans are going to go for shorter arms, but other fancy technologies that will give that better sensitivity. Or LIGO, okay, thanks so much for bringing that up. Yes, squeeze light for both. LIGO is already operating with squeeze light. Actually, yes, well, frequency dependent squeezing. So in a certain frequency regime, you're operating in one quadrature, then you switch the quadrature for lower frequencies. Yes. Yes.
As of last year?
Couple of years. I think it's about 2 to 3 years in my recollection. Frequency dependent last year. Okay. But squeezing, it's been, I think, 2 or 3 years already. Yeah.
What about space-based?
I'll get there. Now, if you thought the LIGO was cool or advanced LIGO was cool, this is what we're aiming for with Cosmic Explorer and the Einstein Telescope. So we're pushing the envelope another couple orders of magnitude. It is pretty challenging. It's also very exciting. Now, going to your question, why space, or what about space? So LIGO and most ground-based detectors will only be able to observe gravitational waves, around a hertz, maybe slightly below a hertz, up to several kilohertz. And if you think just for a moment of these massive objects spinning around each other, emitting gravitational waves in this frequency regime, that means they're about to collide. They're spinning way too fast. These are, several solar masses objects spinning so fast that means they're just going to collide. So what we can really catch from that evolution is just the very end, just a tail of, maybe 100 milliseconds of signal, and that's it. So if we want to observe how those systems evolve, or other systems that are emitting at lower frequencies like supermassive black holes, galactic centers, we need to observe gravitational waves on much lower frequencies, meaning millihertz, sub-millihertz, and so on. There is no way that we can do that here on Earth because of the intrinsic gravitational background that we have in our planet. So the Earth's core is dynamic, it's emitting noise. We can't really do that here. So we need to go to space. And yeah.
Higher SNR. I mean,
It's not the SNR. You're just, well, let's say your noise is a very strong signal. It's overcasting everything else. There's no way to tell it apart. That is the problem. Yeah. So that is why in the early 90s, people proposed formally the LISA mission. LISA stands for the Laser Interferometer Space Antenna. It is a gravitational wave observatory consisting of 3 spacecraft that will observe gravitational waves between about 100 microhertz to about 100 millihertz. These 3 spacecraft are not rotating around the Earth. As you can see here in the animation, they're trailing the Earth around the sun at a distance of about 50 million kilometers. I'll get to that. And they're separated. It's ideally set up as an equilateral triangle with a side length of about 2.5 million kilometers. Now, why 50 million kilometers? Well, we want to, as I mentioned, the Earth is a very noisy place. We want to go away from the Earth. So you may ask, well, if you want to go away from the Earth, why don't you go 100 million kilometers? Why don't you go farther away? Well, we also need to get the signal back. Right? We need to get the data back, not the signal, the data back. And the farther away you go, the more challenges you face in retrieving that data. So it's always a trade-off. How far can I go? How far do I need to go to do the science that I want to do? How close can I stay to make the technical parts feasible? Yeah.
Yeah,
But here you only have one.
That's correct. But what is the reason why I need 2 detectors on ground, at least 2? Because of all the noise on Earth. Here, LISA has a very different situation. LISA is going to be overcast by signal. We're going to have so much signal that, in fact, in some frequency regimes, it's going to be possible to tell apart what are the sources. Well, so do you see? So you have here two tools to do that. One, we're trailing the Earth around the sun. So you get an antenna pattern there. Then you set the orbit of each spacecraft such that the entire constellation is rotating. That gives you another antenna pattern. And that helps you localize the source to within about a degree, which is pretty good compared to LIGO. So yeah, you don't need multiple. So this by itself is a multi-detector system. Yes.
if you treat the Earth as the 4th, I guess another region to represent arms, could you use the new design to filter out any other signals coming through?
Why would you treat the Earth as?
You still have other arms on Earth.
No,
So what about what we were just talking about in the previous slides?
that's LIGO.
Right. I guess what I'm
That is
saying.
completely disconnected. We're not shooting laser beams between LISA and Earth. So this is what happens. So LIGO is going to be observing gravitational waves in this frequency regime. LISA is going to be focused in this frequency regime. Now, there will be some exciting events where we can pick up the signal in LISA, and that may be a source that will also at some point emit in the LIGO band, and we can then track that source, so that system, and tell LIGO, hey, you should be observing the end phase of that system by this date. So there will be some, but not all. For example, galactic binaries. So our galaxy has a supermassive black hole, and nearby galaxies like Andromeda have another supermassive black hole. They're rotating around each other. At some point, they're going to collide in millions of years, but it'll happen. That will never emit in the band that LIGO observes. Yeah. All right. So, okay, it's an equilateral triangle, right? Well, let's think for a moment. So gravitational waves manifest themselves as strain. We don't really measure strain in this case. We're measuring displacement with the laser interferometers, right? So if LIGO needs to measure 10 to the minus 19 meters to observe strain sensitivities of 10 to the minus 20, how much does LISA need to observe if we have an arm length of 2.5 million kilometers? Well, long story short, we need to measure in the order of picometers. And we cannot keep this 2.5 million kilometers distance between the arm lengths stable to the picometer level. Just because of celestial mechanics, this arm length is going to be changing by about 1%. Now, 1% of 2.5 million kilometers is 25,000 kilometers. It's many zeros above a picometer, right? Many, many zeros above a picometer, about 16 zeros above a picometer. So now the trick there is that you can, and we do find orbits that are stable enough that this 1% change in separation occurs in the period of a year. Now, if you convert a year to seconds and then to a corresponding frequency, that falls way below the observation bandwidth. So we're good. So that actually works. Now, that introduces some other technical challenges that we need to address. For example, Doppler shifts. So we have actually some significant Doppler shifts in the laser frequencies. We need to track bit nodes that are changing by about 10 megahertz. We need to measure phase to the microcycle level with changing bit nodes in the megahertz regime. So those are technical challenges that we have to address and that we are addressing. So this is the corresponding strain sensitivity for LISA, 10 to the minus 20 here. This is about 10 picometers. There are various limitations in the frequency bands that limit. For example, here's just shot noise. This is just a limited arm length. If we had longer arms, we could improve this. This is just force noise on the residual force noise on the test masses and so on. I'll get to that. All three spacecraft are identical in LISA. So we carry telescopes, optical benches, gravitational reference sensors, and what we call the MOSA, the moving optical subassembly. So we have a triangle. You have this Y structure. You need to point the laser beams towards the far spacecraft. And well, remember, those arm lengths are changing by about 1%. So that means that this angle is changing. We need to articulate that to shoot the laser beam to actually meet the spacecraft. Now, in the optical bench, we have a laser beam of about 1 millimeter in diameter. Now, as you've probably seen in your courses, this is a Gaussian beam. It's not going to stay collimated, especially not over 2.5 million kilometers. It's going to diverge. So you want this divergence to be minimal. What do you need to do? You need to expand it, right? You need to create a very large waist, as large as you get. Now, of course, you have a finite size spacecraft. How big can you make it? Well, then you go back down to your designs and start playing with numbers and stuff. We ended up setting for a beam diameter of about 30 centimeters. So we're setting up a telescope. It's a very fast telescope, has a magnification of about 130, to take this 2 millimeter or a 1 millimeter diameter beam and expand it to about 30 centimeters to send it out. And of course, you know, it's a Gaussian beam, it'll diverge, and you can do the numbers fairly easily and compute how big the beam will be by the time it reaches the far spacecraft. It's going to be in the order of 20 kilometers in diameter. Now, you do need to articulate that beam to make sure that you hit the spacecraft. You're going to have about 8 seconds travel time from one spacecraft to another. So you do have to have some certain level of control to predict where the spacecraft is going to be by the time the beam actually gets there. And then one of the main challenges here is that you're going to be losing a lot of power. So we need lasers with fairly high stability to do this picometer displacement measurement. Now, those lasers can only provide powers in the order of 1 to 2 watts at the moment. You end up detecting a few hundred picowatts of optical power, and that's all you have. So, yeah. Now, one thing that I should mention is that LISA started originally as a 50-50 partnership between NASA and ESA. ESA is the European Space Agency. As the years went by, that changed due to budget constraints at NASA. So now it is a majority portion of ESA with some contributions from NASA. One of the contributions that NASA will be providing is the telescope. We are part of the team that has been working on the development and testing of the telescope prototypes. One of my students that recently graduated, Callan Jersey, was part of that team developing what we call the optical truss interferometers. So this telescope is a fairly sizable optical system. So it is about 70 centimeters long, about 40 centimeters tall. And as you can see here, it's straight in the path of the laser interferometer. That means that if this element is shifting more than a picometer in the frequency band that we're interested in, it's going to introduce noise. It's going to limit our measurement. So we need to make sure that it doesn't do that. No. And there's a good reason for that. The reason is this. You're losing so much power that it doesn't make sense. Yeah.
What was the question?
If there was squeeze light, if we use squeeze light on LISA.
Not using a squeeze light.
Sorry?
We're not
Using a
using
squeeze light.
We don't use squeeze light just because we're going to be having so severe losses that any squeezing that you can achieve will be long gone by the time you could actually use it.
We're not looking at advantage either, because we're not getting that back to.
Oh, but we are. Just a moment. Okay, let me finish this point and I'll get back to that. I think we're going to stay here for a long time. I'm only on slide 15. Anyways, so this telescope is a sizable part, right? And it needs to be stable to the picometer level. It's not obvious that it's going to be the case. So we in our group developed what we call the optical truss interferometers, the OTIs. These are little Fabry-Perot interrogators that we can mount, if necessary, around the telescope to probe its stability. If the telescope were not stable, then we can then track its deformation and compute out what disturbances are coupling into the measurement. But then, of course, this unit have to be stable to the picometer level at least. And so the work of Kylan in this case was to design, develop, and test these units and demonstrate that they were indeed stable below a picometer. So this was fantastic. Now, going back to Masoud's question, so what are we interfering with? This telescope here is bidirectional. It's not just taking the input laser beam or the local laser beam, expanding it and sending it out. It's also receiving the beam that is coming from the other spacecraft, bringing it down to a couple millimeters, such that we interfere it with the local beam. So if you see here, there is a slight beam coming in that we actually interfere here locally. That is the interferometry that we do. Now, we don't send out a laser beam that we reflect off the test mass, which is the actual gravitational sensor, and send it back out. That, yeah, we wouldn't be measuring any light at that point. We would be counting photons, if anything. So what we actually do technically is we detect the incoming light, the few hundred picowatts of incoming light. We do a phase offset lock to a local laser, basically replicating the phase information of that incoming light, shift it in frequency, send it back out, amplified. And then we do interferometry. Yeah. Now, as you can see, LISA is a challenging mission, right? And there were a lot of concerns on how technologically feasible this mission would be. So that's why both NASA and ESA agreed in the late 1990s to develop a technology demonstration mission called LISA Pathfinder to test three main points that are kind of the hiccups for LISA. One is isolating the gravitational sensors, the test masses, the ones that actually will move, those black dots that will move at the pass of a gravitational wave, to levels of 10 to the minus 15 meters per second squared per root hertz. So it wasn't obvious that this was going to be possible. The other one was conducting laser interferometry to the picometer level with free-flying objects in that case. So we know now that achieving picometer level sensitivity is actually not that tough. We can do it here on Earth. Now, in this particular situation, it was never done before. And then, of course, also testing the actuators on the spacecraft that would enable getting this level of acceleration noise on the test masses. Now, the way you achieve this is not by just letting the test mass there be still. There will be perturbances coming in. So what you do is you have little thrusters, we call them micronewton thrusters, actuating on the spacecraft. So you have the test mass there sitting still, and the spacecraft is just jiggling around, firing these little micronewton thrusters, shielding it from all the disturbances that are coming in. That's how you achieve this level of isolation. Now, LISA Pathfinder, again, is a technology demonstrator. It was not intended to measure gravitational waves. If we wanted to do that, we would have done LISA right away, right? So we took one arm of LISA and shrunk it down to about 38 centimeters. So from 2.5 million kilometers down to 38 centimeters, you can fit that in a single spacecraft. You can see how that is significantly more economical than building LISA. Then you set up a laser interferometer to measure those test masses. So you have two test masses here. You shrink them down to 38 centimeters, have laser interferometers, and sets of thrusters and so on. We launched LISA Pathfinder in December 2015. Yes.
For like the size of your mirrors, the maximum size of the beam waves that you can send out, is all of that dictated by the launch vehicles that are available and the space in them? Or are you guys like operating at a much smaller actual size than what you can fit inside the launch vehicle?
It is a complex problem. There's not one factor. You need to consider all of those factors. So certainly determining launch vehicles, how much mass can we send out there, spacecraft geometries, all of that are factors. And basically, what you can reduce that down is to money. How much is that going to cost, right? And that's where you start optimizing everything. Yeah. The test masses are about, I believe it's about 2 kilograms, if I recall correctly. Well, define quantum in that case. You can, sure. I mean, you could potentially have, optomechanical interaction there. You can actually drive them optically. We did, but it really depends on what you want to test. So, but yeah, you could get to that. Yeah. Okay. Now, so I have a little animation from ESA that shows you what LISA Pathfinder did. So it was sent to the Lagrange point 1 between the Earth-Sun system. It's about 1.5 million kilometers. It is a very quiet place gravitationally. It's a saddle point, so it's not very stable. At some point, the spacecraft is going to go away. But it's for the duration of the mission, it's very stable. You have the 2 test masses separated by 38 centimeters, an optical bench with a set of interferometers. I won't go through all of them. They measure the dynamics of the test masses with respect to each other. Each test mass is housed in their own vacuum chambers. The reason for that is to protect them from contamination during launch and manipulation and such, not because the vacuum in space is bad. All that payload is housed in the single spacecraft. Just to give you an idea of size, the diameter here is about 3 meters. So it's not that big. The optical bench is only about 20 centimeters inside. And when there are any disturbances coming, the little thrusters are firing, making that spacecraft jiggle around the test masses, protecting them. That's what you call drag-free in this case. So this is a photograph of the flight optical bench. I worked on this together with colleagues in Glasgow and Birmingham during my PhD. It is, well, in my opinion, it's beautiful. But when you see this, and after so many years of working on this, this is very fragile. You're gonna have, or it seems very fragile. You're gonna have to bolt it to rocket and launch it, right? So you have to take a prototype of this and do this. And for about, I don't know, a minute or so doing this, you just hold your breath because, yeah, you feel any moment this is going to snap. But no, it survived. And we launched it successfully. We integrated the whole spacecraft. We did what we call space qualification test, thermal vacuum test. This is a test facility in Germany. I was there testing the integrated spacecraft, where we actually demonstrated the displacement and angular sensitivity of the laser interferometer to the picometer level and 100 picoradian level, with everything integrated on the spacecraft in this test facility. So these vacuum chambers here, I believe this one is 6 meters in diameter, have, they call them sun simulators, basically high power lamps to power up the solar panels such that we can operate and run the spacecraft as if it were in orbit. Now, we launched it, and interestingly, the very first measurement that we obtained 4 months after launch was significantly surpassing the requirements of LISA Pathfinder. So again, it is a technology demonstration mission. You want to have an idea that you can actually achieve the technology that you need to do LISA, right? So, but you do relax the requirements, because if you think that you can actually meet those requirements, then you go and build LISA. So we relaxed our requirements by a factor of 10 in sensitivity and by a factor of 10 in bandwidth, keeping that center area there. Now, again, 4 months later, after launch, we were already scratching the LISA requirements. After understanding and doing some calibrations of the noises and all that stuff, we were able to actually surpass the LISA requirements across the entire bandwidth, which was very exciting. Now, what does this tell you? It's not that we did a poor job at designing things. Certainly, we were striving to over-dimension everything to give us margin on all possible fronts to make sure we make it work. Because once you launch this, there's no way that you can go into a lab and say, oh, I'm gonna go there and tweak a little bit the alignment because the contrast went down from 80 to 75%. No, you can't do that. It has to work, right? So we were pretty happy about that. Now I'm gonna start shifting gears to geodesy. But the reason why I'm shifting gears here is because a lot of the work that we've done over the years for LISA and LISA Pathfinder has actually applications in other scientific areas. For example, space geodesy. So mass change, observing how the gravitational field of the Earth is changing over the years. And those are the GRACE missions. GRACE stands for Gravity Recovery and Climate Experiment. It consists of 2 spacecraft on a polar orbit, and they basically just, survey the Earth, measuring changes in the gravitational field of the Earth. the way they do that is, if you imagine you have the two spacecraft that are separated by about 200 kilometers, at some point, you're going to fly over a mountain. That is a big lump of mass. We remember Newton. One of the spacecraft is going to get accelerated towards that lump of mass. The separation between the spacecraft is going to change. And at some point, the second spacecraft is going to feel that lump of mass going to get accelerated towards it. The separation is going to shift. And if you play that game around the Earth, you get a gravitational map of the Earth, right? It's a fairly simple concept. Now, the interesting part is not just that. It's actually when you go and observe over the years how that gravitational map is changing. Because it tells you what is happening with the mass on Earth. So we know that the ice caps are depleting. We have various instruments telling us that, not just GRACE, but also GRACE is telling us where that water mass is going and help us identify, for example, flood zones, and many other, feed us with information and data to make in part also policy decisions about relocations or hazards and so on. Now, there are two GRACE missions so far. The first GRACE mission was launched in 2002. It consisted again of basically this identical pair of spacecraft, measuring the ranging between the two spacecraft with a microwave instrument to about to the micrometer level. Well, there around, I think, 2008, the community was starting getting anxious. The geodesy community was starting to get anxious about the continuity of GRACE because it had already been in flight for about 6 years. The nominal lifetime of the mission was 5 years. It actually lasted until 2017. Now, there are some technological improvements that people wanted already to incorporate here. For example, improving the interspacecraft ranging. So in LISA, we're doing picometers, right? So instead of doing a microwave instrument, we can consider inserting a laser interferometer, right? And that's exactly what we did. In the second GRACE mission that was launched in May 2018, called GRACE Follow-On. I know it's a very inventive name, but it is really called just GRACE Follow-On. We incorporated a technology demonstrator to have a laser ranging interferometer to measure the interspacecraft separation. And that improved the displacement sensitivity by about a factor of 1,000. Now, it's not going all the way down to a picometer. It doesn't really need to go all the way down to a picometer in this particular situation. But it is limited to about the nanometer level because of the laser frequency noise. So the frequency is just fluctuating so much that that will just limit the displacement sensitivity to that level. It is exactly the same laser that we used in LISA Pathfinder, very similar to the laser that we will be using on LISA. Now, on LISA, we have 3 spacecraft, and by having 3 spacecraft, we can play other games, we can do other tricks to subtract down the laser frequency noise and achieve picometer level sensitivity. We don't have that in GRACE. Yes? They send up 2 new satellites because the old satellites, the batteries were dead. Many of the instruments were already way past their lifetime. Yeah, it died. So this is for example the sensitivity of the laser interferometer. This is an actual signal of an actual measurement of the gravitational signal from GRACE Follow-On using the laser ranging interferometer. Now, GRACE is measuring changes in the gravitational field of the Earth. You want to measure gravity. But as you can imagine, there's solar wind, there's drag, there are many other effects that will imprint accelerations on the constellation that are non-gravitational. So there, you need to incorporate in the spacecraft very high-performing accelerometers to measure those non-conservative forces and subtract them out from the overall measurement. It turns out that in both missions, in the first GRACE mission and also in GRACE Follow-On, those accelerometers have failed. So in the GRACE mission, one of the accelerometers just started exhibiting significantly higher noise. In GRACE follow-on, one of the accelerometers in the second spacecraft, in spacecraft B, completely failed. Now, the community was able to come up with tricks to rescue the mission, and we are getting good data, but that is certainly not a situation you want to be in when you're paying $600 million for a mission. Yes?
Accelerometers tell the difference between a gravitational acceleration and something else.
Well, in this particular case, because they do measure those non-conservative forces, they're not sensitive enough to the gravitational baseline. So that gravitational baseline comes from that gradient measurement that you can do with the two spacecraft separated. So that those two spacecraft are your gravity sensor. Yeah. Great question. Yes.
Oh, man.
Well, the trick is, and this is nasty, it's actually pretty smart. The trick is that you take the signal from the first accelerometer in the first spacecraft and delay it in time to transplant it to the second spacecraft, considering some other effects. No, you have to make some assumptions, but not everything. You have metrology to do a good transplant of that information, but it's far from ideal. Yeah. Sorry? Oh, I couldn't tell. I mean, we're looking at a degradation of maybe an order of magnitude or so. Yeah. Yeah. So now something that, and now I'm getting into the stuff that we do in my group. Something that we've started working a few years ago is in the development of optomechanical inertial sensors, optomechanical accelerometers. And the concept that we've been working on is very simple. So we have this mechanical resonator, a test mass supported by two leaf springs attached to a base that basically just will move left and right in this case at the presence of an external force. Very simple. Now, the interesting part comes in how do you fabricate this? So we're making it from a monolithic piece of material. It's not like we fabricate the test mass, the leaf springs, and the base separately, and then we glue everything together. So everything is fabricated monolithically from a single wafer using materials that are very low loss mechanically that would yield very high sensitivity to external accelerations. So a figure of merit for determining the losses in a mechanical system is the mechanical Q. So this resonator here is a 5 Hertz resonator, well, 4.7, with a Q of almost 500,000. So it's a very low frequency with a fairly high Q. It is very sensitive to accelerations. We measure the motion of, and of course, the way you measure an acceleration in this case is by using a laser interferometer in our case. So most of the accelerometers that are used for GRACE applications are using electrostatic plates, but they're not sensitive enough. So they measure perhaps displacements in the nanometer regime, maybe hundreds of picometers. We need to measure sub-picometer in this case, as I'll show you in a moment. We've also developed this, what we call quasi-monolithic optical heads as our laser interferometers. Here's a penny to give you an idea of the size. And this is a chart giving you a comparison of what we expect our sensitivity to be in comparison to the dashed lines, which are the accelerometers on GRACE. This is an actual measurement from the lab. The other traces are, I'm not going to get into that. I'll keep moving. Oops. Hold on. Sorry, what happened here? Here we are. This is a photograph of the prototypes we've developed in the lab over the years. This is what we call our TRL prototype, 2 mechanical resonators. We've developed the fiber injectors, resonators, optics, and such. And we've estimated from our measurements that we are achieving sensitivities in the order of 8 picog's above 60 millihertz, which for a system of this size is very good. Yeah. What's the limiting factor? In this case, right now, we've been mostly limited by the interferometer, in fact. So and actually, let me actually go to the next slide to show you how good our interferometer needs to be. So we need an interferometer that measures about a 10th to maybe, 50, a factor 50 better than a picometer. So it's been done before. LISA Pathfinder achieved it with that optical bench. So we have a notion of how to get there, but it's not trivial. So this is the displacement sensitivity that we need our interferometers to provide in order to observe the thermal noise of the mechanical resonators. Yeah. Yes.
Sounds like
One of the issues is the secondary sensors on the GRACE device. Is there any investigation to co-design some of these optomechanical operators with these? Oh, is that an accident?
That's exactly what I'm showing here. Tal.
Exploration of two test misses.
No, that's just one. That's just one.
We actually have a laboratory and pico-G acceleration.
We've played some tricks, and I'll get to that in just a moment to show that. Yes. So this is the optical head that we developed in one of my other PhD students. It was primarily her PhD thesis. This is the setup that we put in our lab to test it. Here's the little interferometer. Here's the mechanical resonator. A lot of optomechanics to inject the laser beams, collect the laser beams, fiber optics, and so on. This is inside a vacuum chamber. This vacuum chamber here on top of the optical table, resting on pneumatic feet. On a separate foundation, you can see a little gap here from the rest of the building to decouple it from seismic. We've done everything we could to isolate this as much as possible. We also purchased a commercial seismometer with fairly high sensitivity to have some type of reference and kind of validate the signals that we observe, right? And this is a very busy plot, but I'm going to walk you through it. This is what we measured. The black trace is coming straight out of our system. The yellow trace here is coming straight out of the commercial seismometer resting on top of the vacuum chamber. Now, interestingly, we kept observing this feature here, and we didn't know exactly why. So you can actually estimate from first principles what is going to be the performance of your accelerometer. So you know how well your interferometer performs. You know what is the thermal noise of your mechanical resonator. You do the math and say, okay, I need to be measuring this level of acceleration noise. We kept getting stuck at this level, which was several orders of magnitude higher than where we should be, and we didn't understand what it was. And on top of that, we kept observing this feature here, and we didn't really know at first what it was. So we started doing some digging. At that point, as Dal mentioned at the beginning of the talk, we just came back from Texas. We did these measurements in Texas. We were in College Station, Texas, about 130 miles direct line of sight from the coast. What's happening here is that if you imagine you're sitting on the beach and you're looking at the water, the waves coming in, crashing at the coast, recoiling, crashing at the coast, they're creating acoustic waves that propagate through the landmass all the way to our little basement laboratory in College Station, Texas. And if you just picture that in your mind, what is the periodicity of that? 1 to a few seconds, right? Let's say 1 to 10 seconds, which is exactly this. And that, of course, we should have known this. Had we known a little more geophysics, we would have been able to identify this right away. This is very well known. It's the microseism. Again, it is very well known, and it is a very distinct feature. And both measurements lined up perfectly. It's not that we're taking the commercial seismometer to calibrate our system. This is just straight out comparison, and they line up perfectly. Now, towards lower frequencies, they don't. And there are certain effects affecting our system more strongly than the commercial seismometer. One of them, for example, is at these low frequencies turn out to be pressure. So inside our vacuum chamber, and I don't know that you can see this. Actually, maybe you can. So this is a little steel wire that we use to, well, that we have a set of steel wires suspending the platform inside the vacuum chamber to provide some additional seismic isolation. So what happens is that when the barometric pressure changes, when weather changes, the pressure of the earth of the air in the lab changes. Applying a spurious force on this platform, making that platform swing a little. And we were able to verify that and correlate that with weather data from the airport in College Station. And that explained the effects here at 10 to the minus 4 hertz. No, you can't. I mean, that is actually force acting on the platform. It's not the pressure changing in the chamber. It's, something pushing the platform, making it wiggle. That is the changing barometric pressure. So it turns out that at some point we proposed to NASA the idea of, hey, we have these neat devices. We want to turn them into accelerometer systems for mass change for future GRACE missions. So we proposed this IIP project to NASA back in 2021. We're very grateful that we were granted the project, and we started turning this into something like this. And at this moment, this is looking like this. So we're making good progress. There's still a lot of work to conduct to finalize this triaxial system. Triaxial, you have one accelerometer here, you have another accelerometer here, and perhaps you can distinguish an out-of-plane resonator right here. 3 interferometers. This one here is going through this pentaprism. Some of you may remember the class of yesterday. Pentaprism going down here to the test mass, coming back out at exactly 90 degrees. That's why we use a pentaprism. And here is a penny to give you an idea of size. So this is an entire system weighs, if I recall correctly, maybe Andrea can correct me, in the order of 400 grams, which is very, very low swap, very low weight and size and mass for an accelerometer of this sensitivity. Now, we advanced this top plate, what we call the XY stage, XY, to what we call a TRL5 prototype, TRL in terms of how mature this particular system is. And something that we realized along this project is that if you take arrays of accelerometers and put them together, you can actually have a full IMU, not just a triaxial accelerometer. You can measure acceleration along all 3 degrees of freedom, but also measure rotations along all 3 axes. And that's another concept that we proposed to NASA a couple of years later, actually last year, for a test flight. And we call this ODIN. ODIN is the Optomechanical Distributed Instrument for Inertial Sensing and Navigation, which takes basically 6 of those XY stages with some modifications, assemble them in a type of cube that will give us not only linear accelerations with the sensitivities that we need for comparable to GRACE, but interestingly, and this was a surprise to us, also measures angles way better than, for example, a laser fiber gyro, which is the go-to technology nowadays in spaceflight, in aerospace. And so this here in purple is the laser fiber gyro flying on GRACE follow-on right now. This dashed line is where we expect ODIN to perform in terms of angular measurements. So several orders of magnitude. At very low frequencies, well, this is very steep. This slope is very steep. That comes from the fact that ODIN measures angular accelerations. In order to determine angle, you need to do an integration twice. Laser fiber gyros measure angular velocity, so you only have to integrate once. But in this regime, you're relying on star trackers anyways. So overall, this could be a significant improvement in terms of technology. So we proposed this to the INVEST program at NASA last year, and we're very grateful again that we have been funded to fly this in about 3 years' time from now. It is a very aggressive flight program to develop an instrument in that short a time. We actually need to be delivering this instrument in spring 26, so a year and a half from now. Oh boy, it'll be fun. Now, this type of technology has, of course, other applications, not just for earth sciences. I'm not going to go through all of them, but also for engineering as a general IMU. You can put this on a spacecraft, on a submarine, and you have a very good IMU. You can deploy this on planetary systems as seismometers and such, which, of course, as you have probably seen in the news, it is a very active area right now of exploration, not just for building, for example, colonies on the moon, but also for exploring planetary systems like Venus, Mars, the moons around Jupiter and such. And with this, lastly, I just want to acknowledge my team. They are the ones actually in the lab getting results and nice charts for me to show you and I guess brag a little bit about. I want to thank also our sponsors and our collaborators, and thanks so much for your attention. Sorry it took me so long.
Yeah, very exciting. Obviously, you have a timetable to talk about or find that there were ideal geometries for and mixing of signals or improving your revision.
Yes, that is an active area that we're researching, and not just orientations in arrays, but overall processing, Kalman filtering, and so on to optimize the data streams and get the best performance out of the system. Yeah, that's something we're looking into. Yeah. Yes.
I assume it's impractical for LISA to have very high power lasers burning a hole in vacuum as a waveguide instead of expanding it.
Oh boy, I don't know. I'm not familiar with that. I don't know if it's possible or if you're just gonna buy more trouble. But I mean, those would be non-linear effects, right? So
You won't get those in space. There's no index for you to have occur non-linearity.
Yeah.
Well, as I understand it, Deals in UNM is doing this. I know he is doing it. I don't know if it's practical yet.
well, but I guess primarily, you need to remember we need to go back to doing laser interferometry. So you have to have a laser that has the right properties to get the displacement sensitivity that you need. And if there was a laser with higher power that we could use for this, we probably would be using that. Because 1 to 2 watts is not that much power. It's not that we're concerned about thermal effects or thermal lensing on the components yet. That's not the problem. It's just really getting the stability that we need. Yes.
You were measuring the gravity variations on the surface of the Earth.
Yeah.
Your satellites are going from the North Pole to the South Pole. How often do you go over the same region again?
Once a month.
And when you go over the same region, do you measure the same signal?
Well, no, it's changing over time, and
Because your measurements are not accurate, or because the Earth is changing?
because the Earth is changing. And but that is a great point. So it's going through that location only once a month. There's a lot of things that we're missing. There are aliasing effects that are actually the next limitation that we need to address. So NASA, together with DLR in Germany, are going to launch a third GRACE mission called GRACE-C, GRACE Continuity. Again, they're great at picking names. So it's going to be launching in 2018, but it's just going to be a single pair. Now, currently, ESA is working on what they call NGGM, the next generation gravity mission, which is another pair that if all the timelines and the development lines up well, it's going to be on an incline orbit. And if you have that, you can reduce the coverage to about a week, and then address that aliasing problem.
As a follow-up to that, what would be the actual spatial resolution of readings? Because I'm familiar with the GRACE climate products. like presentation, so how well can you resolve those?
So with GRACE, you can do about 300 square kilometers. If we actually manage to do that configuration, I have to say, I don't know. I have to look it up.
A few questions, but we're coming up on the hour. The only comment I saw here before the computer died was you need to wrap up. And that was to me, of course. So I'm going to wrap it up and thank our speaker. Here, of course, our second certificate.